Okay, I'd like to introduce people to the notion of blockchain. There's so much written about it, but it's all kind of talking about how it's going to change society and so forth. It's very difficult to actually know what it is and whether it's actually appropriate to a particular problem. So in this presentation, I hope to explain what the technology is and what the properties of the technology are. So what is blockchain? Well, it's just become a buzzword. There's all sorts of articles about how it's the biggest advancement in technology since the internet, that it's being considered for all sorts of problems like IoT and voting, and my favorite one is, this was a real article, it's being considered for protecting our nuclear technology. Even the US military is looking at blockchain technology to secure nuclear weapons, and after this talk you can sort of judge whether this is really the best possible solution for that. So what is it exactly? Well, there's the specific technology behind Bitcoin, but people say, well, that's just Bitcoin, we can modify it, in which case it becomes very blurry about what is blockchain versus anything else. And I've seen it kind of applied to any design that includes computers, networks, and crypto. So it gets extremely confused about what it actually is, or anything that offers the API of storing and retrieving data. So it's really impossible to know what a generic blockchain system is. But it is possible to describe Bitcoin's blockchain, and that's where the term was coined, so I'll explain that. So Bitcoin was a paper in 2008 by some pseudonym, and it was released as open source software soon after. There wasn't like a specification. Instead, the code is how it works, and the community, the open source community, can agree on modifications, so the details might differ. But if there actually were a spec with a lot of different incompatible in any subtle ways implementations, that would be a real disaster. So the main design goal behind this, and it's an extremely clever design given the design goal, was they didn't want to trust any known organizations, no banks or governments, in order to prevent the government from doing things like collecting taxes or following a money trail or not letting you pay money to certain countries or organizations. Now, whether or not that's a good set of goals, they came up with a solution for that. So trust is given to a large community of anonymous things called miners. Anyone can be a miner. You just download the software or you buy a specialized mining rig, and miners are rewarded based on doing a lot of computation. And the security assumption is that the set of honest miners will have more compute power than the rest of the world can collect. So if you go to Amazon, you can actually just look at the various types of miners, and you can buy a specialized mining thing. Now there's this thing called the ledger, which sounds like a very fancy word. It's just a log, an append-only log, which is the format of all of the data associated with it. It's a set of transactions, where a transaction basically says that one public key pays some other public key some amount of Bitcoin. So the format of the ledger is as a chain of blocks, and that's kind of where the term blockchain came from, where what a block looks like is it includes the hash of the previous block, a random number called a nonce, the miner's public key, and then a bunch of transactions. So a transaction says that public key X is signing over what public key X received in some previous transaction, which is indexed by the hash of that transaction. So in this case, if you notice, the top line says that, the third line says that from transaction with hash X15, which is the first line, A pays C 74.21 Bitcoins. So where did A get those Bitcoins? Well, it got it in the first line. So now on the first line it receives 74.92, but in the third line it's only paying 74.21. So the difference between what it received and what it's sending out is known as a transaction fee, sort of similar to the 3% that the bank might take on a credit card transaction. So now you can also have multiple outputs. If you don't want to sign over all 855 Bitcoins that you receive, you could, and you only want to pay 25, you can pay yourself change, or you can give it to multiple recipients. So what exactly is a ledger? It's just a log that the only thing you can do is append to it. There is distributed database technology that's been around for decades, and it's way more flexible. It allows multiple nodes to update the same section of the data, and you do that with locking, or it allows atomic transactions where there's several sort of things that have to be done, and you only want any of them to work if all of them have worked. So that is done with two-phase commit. Anonymity, Bitcoin is not really anonymous. Even though you don't use names and you use public keys, there's a lot of information that can be mined from looking at the ledger, because every transaction ever since Bitcoin was invented is in the ledger, fully world readable. And that's actually kind of how the world figures out how much money is being paid in ransomware, because they can pretty much figure out from the kinds of transactions what things are probably ransomware. Now, what's a valid transaction? Suppose A pays B, the output of a transaction with hash X. How can B tell if the transaction is valid, that he's actually going to get paid? So, first, the transaction where A paid B has to be validly signed by public key A. That seems fair. But B has to somehow find a transaction somewhere in the ledger with hash X to make sure that A actually owns that amount. And then he has to search every transaction since that one to make sure A hasn't paid that transaction over to somebody else. And until the transaction is solidly in the ledger, and I'll explain what that means, A can double spend and cheat B. So the merchant kind of knows he's going to be paid. But what about the customer? What recourse is there if the merchant never ships the merchandise? If you have no known entities in here, there's no one to complain to. Whereas something like eBay, there is somebody that can mediate disputes. Now, what if we didn't have blockchain? Well, if you had a central thing that determines which things are legal and how much money each public key has, it would make having a ledger very easy to do and very efficient, and it could mediate disputes. But suppose, and if that entity misbehaved, it's well known, so you could sue it if it was discriminating against certain transactions. Or if you want to say, well, I don't want to trust any one organization, you could have a consortium of known organizations, some handful, maybe 20 of organizations. And if the only reason you have more than one is because you're afraid the one might not be available, then you could have any one of the organizations sign your transaction and it would be valid. But if you want to guard against having some minority of them misbehave in some way, then you could cause your transaction to have to be signed by a majority of the entities in the consortium. And again, this will be, it will be way more efficient in terms of compute, bandwidth, storage, and latency, and allow the adult supervision that most applications require. So, how does Bitcoin do it if there's no known organizations? Where do Bitcoins come from, and how is the ledger agreed upon? So, blockchain is a set of blocks, and it's the format of the ledger. A block is a set of new valid transactions that should be added to the blockchain, but the block is specially designed so that the hash is extremely hard to compute. Now, Bitcoin tries to cause a block to be added by the community of miners about every 10 minutes. And if the blocks are found too quickly, less than 10 minutes, then the hash difficulty is increased. And if too slow, the hash difficulty is decreased. And this is kind of cool. How do you actually adjust how hard it is to create the hash? So a cryptographic hash is a kind of mathematical thing. A good hash is sort of like a random number, where as if for every input, it's a totally a different random number that was generated. So if you wanted a block to have a hash with the top bit being 0, you'd have a 50% probability that the top bit would be 0. If you want the top 10 bits to be 0, you'd have to play around with different blocks and different random numbers, and you'd have a 1 in 2 to the 10 chance. So the way to adjust how hard it is to come up with a block with a hash is to adjust the maximum size of the hash, or the number of leading zeros. So currently the hash has to have 70 leading zeros, which 2 to the 70th is an extremely large number. Now, how do you find a block with a hash with 70 leading zeros? Well, you insert a bunch of valid pending transactions, you choose a random number for the nonce, you compute the hash. If it doesn't have 70 leading zeros, which with a probability of 1 minus 1 over 2 to the 70, it won't, choose a different random number and repeat about 2 to the 70th times. If you're lucky enough to be the first to find a next block with a small enough hash value, you'll get rewarded with some bitcoins. So currently the reward is 12.5 bitcoins plus any transaction fees, if you happen to be the lucky miner that found a block with the random number that has the right hash. So what's the purpose of all of this hashing, which is estimated to be 4 times 10 to the 18th hashes per second? The assumption is that the community of miners is so large and has so much collective compute power that no dishonest entity will be able to collect enough compute power to have more. So suppose a set of miners had more compute power. Well, then they could undo transactions and create an alternate history. They could discriminate against certain transactions and refuse to ever include them. They could double spend their own money by creating an alternate chain, and this would bring down the whole Bitcoin concept. Now, if you look at traditional integrity checks, blockchain is done with no secrets, but traditional cryptography uses a secret, like a private key, in order to generate the integrity check. And the math works out such that it's trivial to compute the integrity check if you know the secret, but computationally infeasible to forge it if you don't know the secret. So there's a huge gap between the people who are authorized to create a signature, the amount of compute they require versus the amount to forge it. So good guys are those that are supposed to be able to generate the integrity proof, and bad guys are those that want to forge it. So in traditional cryptography, you make an enormous gap between how much computation you need to, if you're a good guy versus a bad guy. And increasing the key size makes the gap even bigger. So for a 1,000-bit RSA key, forging a signature is about 2 to the 63 times harder than generating a signature. And a 2,000-bit RSA key, forging it is 2 to the 94 times harder. So it's very difficult to actually be able to understand these numbers. So a different way of putting, and with blockchain, it's equally expensive to compute for both the good and the bad guys. So another way of saying it, with RSA signing versus forging, with a 1,000-bit key, signing takes about 1 millisecond on a typical CPU, whereas breaking requires the entire current Bitcoin miners community's computation for an hour. Whereas if you double the key size, it takes about 6 times more to create the signature, 6 milliseconds, still trivial, but breaking it would require the compute power of the entire Bitcoin miner community for the next 1,000,000 years. And again, blockchain is equally expensive to sign as to forge. So the fundamental novelty of blockchain, I claim, is that it's an integrity proof that uses no secrets and no known trusted entities. It isn't that you have data formatted as a chain of blocks in an append-only kind of fashion, and it's not that its data is stored in lots of places. It's not that multiple cooperating nodes maintain the database, and it's not the concept of having integrity proof on the data, which is where the term immutable comes from. So what is immutable? It means it's unable to be changed. Is the blockchain immutable? No, it isn't. With an integrity check, I mean, you can certainly change the data, but with an integrity check, it can't be changed without detecting that it's been changed. But I claim a traditional integrity check would be way more efficient than one that's equally difficult to compute as to forge. But also, with blockchain, someone can decide to roll back the ledger, and it has happened. So how can the ledger get rolled back? So there are these things called forks, and I'll talk about 3 different types of forks. So a fork is where you have a chain of blocks, but it can diverge into 2 different valid chains. And how can that happen? Well, with a temporary fork, it's possible for multiple miners to semi-simultaneously find a hash, which means that there'll be 2 different valid chains. Now, if a miner sees multiple chains, it starts working on the longer one. So you hope that eventually everyone will agree on one chain. But this can take several blocks because of the internet taking a while for things to propagate. So the advice is not to consider your transaction complete unless your transaction is recorded in block N and the chain has 6 more blocks after that, which means you can't really feel safe until an hour after you've done your transaction. Yeah, because before it's actually really in the ledger, A can double spend and cheat you. So the way these things propagate is via gossip. So basically, every miner is configured with the IP address of a bunch of other miners in some sort of kind of haphazard way. And the more kind of loops you have, the more inefficient it will be as things keep getting transmitted multiple times. But also, it might be very fragile. So in this particular little gossip network, if that node dies, there will be a partition until that node comes back up. If the internet is actually partitioned or the gossip network is partitioned, miners on either side will happily be adding blocks to the blockchain. When the partitions rejoin, whichever side has the longest blockchain would win. Everything beyond the fork in the losing blockchain is no longer in the ledger. Any bitcoins that were mined are not there anymore. Any transactions in the losing fork are no longer in the ledger. And any payers in transactions in the losing fork can respend and cheat whoever it was that thought they were paid. There's also unintentional forks that could be permanent. So in March, there was an incompatibility in the software such that there was a transaction that looked invalid to the old version of the software, in which case they would completely reject any blockchain that had that invalid transaction in it. So this would have lasted forever, but somebody noticed and made a decision as to which chain to choose. So whoever this somebody is made a decision that affected a lot of people monetarily, because any blockchains and any blocks that were mined in the losing one, whoever had mined them loses all that money, and transactions that were logged no longer are logged. Another kind of fork is an intentional one, where there's a sort of copy of Bitcoin, which is known as Ethereum, where they had this thing called smart contracts, where they say they don't need any lawyers, the code speaks for itself. So somebody created a contract for some sort of distributed autonomous organization, And there was a bug in the code that defined that organization, such that even though they raised $150 million worth of Ethereum, someone noticed a bug where he could siphon out the money to his own account. And so then they had a choice. Should they let the guy who noticed that keep millions of dollars, or do they roll the ledger back by weeks? And so they made the decision to roll the ledger back by weeks, which means that this concept that you don't need any lawyers, the code speaks for itself, was not really true. But it also means that not only did the DAO hacker lose all the money, but a lot of perfectly honest miners who had been mining on that lose all the Ethereum things they had mined. Yeah, supposedly there's no one in charge of blockchain. It's a completely democratic group of autonomous miners, but somebody makes the decision and convinces everybody else. So anyway, there's a finite total number of bitcoins they've decided, whoever did this. So every 4 years they have the amount of bitcoins that you get for finding a block. So it started out as 50 and now it's at 12 and a half. And 2140 it will be zero, but long before then it'll be negligible, like 1,000th of a cent or something. So Bitcoin claims that transaction fees are lower than like with credit cards. And today that is true because most transactions, it's optional whether to put in a transaction fee. But if there got to be too many transactions to fit into the block, miners will only include transactions with the highest transaction fee. And as the reward depends on fees rather than on mined coins, the transaction fees will escalate. So currently the amount of that the miner is rewarded is about $8 per transaction if you add in the block reward plus the transaction fees. So that means that when the block reward gets to be zero, the average amount of transaction fee will have to be about $8 to make up for it. So there's all sorts of interesting statistics on the web. So another interesting question is how much energy is being consumed by this? So it's been reported that miners barely break even on what they pay for electricity. So given that, currently the mining community is rewarded about $2 million a day, which translates into a nuclear power plant is being used just on all the hashing involved in blockchain. I claim this estimate might be low because if you buy a mining rig, you're going to want to use it even if you're losing money on electricity. Or you may not know how much the mining is costing you because you don't very carefully look at your bill. Or if someone else pays the electricity. Now, why would that be? Well, if you break into machines and have them mining for you, which is a common thing for bots to do these days, or create an invalid public cloud account with a stolen credit card number, which doesn't get noticed immediately, or if you're living in your parents' basement. So it's harder to win against specialized mining machines with an all-software solution, but if the electricity is free, then hey, why not? So how much storage? Well, currently the ledger is 103 gigabytes, and it's up about 40 since last year. And the most it can grow is 50 gigabytes, except that they're talking about increasing the block size, in which case it would be even more than that. And this is stored at every full node, and nobody knows how many full nodes there are, but people know that there's at least 6,000, and estimates are that there might be as many as 30,000. So, but I suppose we're a storage company, so it's all good. And it's also hard to protect your bitcoins. It's just a data structure on your machine. If you lose your data, all of that money is gone. Or if somebody breaks into your computer, they can steal your money and spend it before you can. With banks, there's some legal protection of user money. So what exactly is a generic blockchain? It's easy to clone the code and then do modifications. So what is the intrinsic blockchainness that did not exist before this, and how much can it change and still be blockchain? So basically, I don't really know. So now there were public blockchains, and now there's like private blockchains where this confuses me because if you know the organizations that are running the blockchain as a service, you can do traditional cryptographic things. So at any rate, that's um, yeah, any of these technologies could be used privately as well. So technology is often hyped without any explanation of what it actually is and how it compares to other things. Often it's a moving target, and the hype might be sufficiently successful that calling things blockchain might be the right thing to do. And I don't care what things are called, I just care about the security and efficiency properties. So my advice for designs is don't say, here's a solution, let's see if we can apply it. Instead, start with understanding the problem you're solving, then consider several types of solutions and compare them. And don't say, can we use this particular technology? So I could, if people want to explore this, I would love to be involved in kind of trying to decide what really are people trying to do and whether there's other technologies that we might want to do. So feel free to contact me and we can have a little email discussion. That being said, there's also a group at Dell that understands all of these software things like Ethereum and Hyperledger and stuff, and everything works fine on Dell hardware. So if you actually do want to use or experiment with these, then there is a group that can help you do that, and you can send to that email address. So thank you.